Hello, this is section 2.8, one-to-one functions and their inverses. Okay, so to start, we need to remember what a function is. So a relation is a function if every x in the domain is paired with only one y. In other words, when you have a function, the x's must be different. All right, so to test that, we use something called the vertical line test. We put our pencil and run it vertically through a function. If that graph only passes the vertical line in one place, that ensures that the x's are different and we have a function. All right, so a new definition is a function is one-to-one on a domain D if each value of f of x or y corresponds to exactly one value of x in D. So that means that you've got a function, so the x's must be different. Well, if it's a one-to-one function, the y's are also different. And then that makes the function one-to-one. Each x is different and each y is different. All right, so we have a test for that, and that's the horizontal line test. So we have the vertical line test for this function here, and it's only passing through my pencil one place. That's a function. Then we have the horizontal line test, and right here you can see that when x is 0.469, y is 1. When x is 5, y is 1. When x is 8.531, y is 1. So the y's aren't different. It fails the horizontal line test because it crosses that horizontal line in 3 places. So this is not a one-to-one function. All right, let's see if you can understand by pausing the video, see if you can say which one is a one-to-one function and which one is not. All right, this one is one-to-one. So this is an exponential function. All exponential functions are one-to-one. This one fails the horizontal line test. This is not one-to-one. This is absolute value function. It is not one-to-one. This is a polynomial function. It is not one-to-one. Okay, why is this so important? Well, one-to-one functions are necessary if you want to have an inverse. So here is the definition of inverse function. Let f be a one-to-one function with domain A and range B. Then its inverse function, and that notation is f to the negative 1. That's the notation for inverse of f. Has domain B and range A. So the domain and ranges flip. And it's defined by this. The inverse of y is equal to x. And f of x is equal to y. So what that's saying is that the ordered pairs switch. So if you have the ordered pair xy in f of x, then the ordered pair yx is going to be in the inverse. So the ordered pair switch. You have to have a one-to-one function to have an inverse. Okay, so here is a picture just showing you that the domain of f gives you the range of f, input, output. And the inverse takes that range and it becomes the domain of the inverse, and that's the range of the inverse. So the notation that we're going to use to relate a function f to its inverse is to let the inverse of f be denoted f to the negative 1, and you have to use that notation. It does not mean f to the negative 1 does not mean 1 over f. It just means f to the negative 1 is the inverse of f. Okay, so there are 3 properties of inverse functions. Inverse function property, Let f be 1 to 1 with a domain of A and a range of B. The inverse of f satisfies the following cancellation properties. The inverse of f of x. So this is function composition. This is saying if you put f of x into its inverse, it's going to spit out x for every x in the domain of A. Same thing, if you put the inverse of the function into f, it's going to spit out x for every x in B. So that's the inverse function properties. Okay, so let's look at an example. So f of x equals x minus 3 quantity squared plus 5. And g of x is equal to the square root of x minus 5 plus 3. They are inverses. You can tell they are if you notice that this has x, first thing that's happening, x minus 3, then it's being squared and then added 5. If we reverse and change the order, this has x minus 5 first, then the square root, which is the opposite of squaring, and then adding 3. So it's completely opposite signs, opposite operations, and in opposite order. But we can show that they are inverses of each other using the inverse property. So first thing I'm going to do is put g of x into f. So g of x is all of this, so this is going to go in place of the x. So we've got the square root of x minus 5 plus 3. That's in place of x, then minus 3 squared plus 5. So if we do that, that's going to be this 3 minus 3, that goes away. And then the square root of x minus 5 squared, I'll go ahead and write that out, is just x minus 5 plus 5, and then that gives me x. So it spit out x. All right, we're only halfway done. Now we have to put f into g and see if it works. So we're going to put this whole f into that x right there. So that's the square root of, parentheses, x minus 3 quantity squared plus 5. That's my x. Then minus 5, all under the radical, and then plus 3. So that would be 5 minus 5, that's 0, and then the square root of x minus 3 squared plus 3. I'm going to square root that square, that gives you just x minus 3 plus 3, 3 minus 3 and plus 3 is 0, and you get x. So we have just shown that f and g are inverses. All right, that's property 1. Property 2, the graph of the inverse of f can be obtained by reflecting the graph of f over y equals x. So the line y equals x, it's a really important line. It's called the identity line. When x is 1, y is 1. When x is 2, y is 2. So forth and so on. So that's the identity line, f of y equals x. And here is the function f. And you see how each one of these points here, every single point is directly across. That means this is a right angle right here. And this distance equals that distance. So if I were to fold my paper on this line y equals x, this blue function would fit right on top of that red function. That's a property of inverses. The reason that is happening is because if AB is a point on f, then BA is a point on the inverse of f. All right, and then I'm going to add a D. This is because the domain and range switch. So that was the definition of inverse. If f has domain A and range B, then inverse of f has range, has domain B and range A. The entire set of x coordinates becomes y coordinates for the inverse, and vice versa. So this is one specific x and y. They switch and become yx. So each individual ordered pair switches, and the entire domain and range, they switch. Okay, so the next, finding the inverse, graphing and stating the domain and range. So we're going to use these two right here, C and D, a lot for this next piece where you just are given a graph. So it says, let the following graph represent a one-to-one function, f of x. The domain of f is -2, 7, as you can see. So it starts here at x equals -2, and it continues until you get to 7. And the range, you can see, it starts at 0 and goes up to 3. The 3 right here. So determine the domain and range of the inverse. Well, that means that the domain of the inverse is going to be the range of the function. And the range of the inverse is going to be the domain of the function. And then, in fact, you can graph the inverse really easily by just taking the points that you're given. You might have to read off the graph, but this time I've written it. So -2, 0, 2, 2, 7, 3. I can use that to find the ordered pairs on the inverse by just switching. So 0, -2, 2, 2, and 3, 7. And if you graph that, I don't think it's quite going to fit, but here's 0, -2, here's 2, 2, and 3, 7 would be up here, but I can sketch it. You can see that it is symmetrical about the line y equals x. All right, example 2. Let the following graph represent a one-to-one function, f of x. The domain of f is -1 to 2, and the range is -3 to 1.5. Graph the inverse and determine the domain and range. So this time I wrote out the ordered pairs. So the inverse ordered pairs would be just these ordered pairs switched. Okay, so 0, 1.5, and 1.52. And then we can graph these ordered pairs at -3, -1, -2.50, and then 0, 1.5, and then 1.52. All right, so we can remember that the domain and the range are going to switch, but sometimes people switch the individual numbers, which isn't right. So I'm going to look at this new inverse graph and write down the domain by looking at it. So the x coordinate farthest to the left is -3, and then the x coordinate farthest to the right is 1.5. So this used to be the range of f, and now it's the domain of the inverse. And so these inside numbers don't get switched. And the range of the inverse, if we look at the graph, we can see we're coming down here. The lowest y coordinate is -1, and the highest y coordinate is 2. All right, now let's talk about something that I didn't notice before. It's really hard to notice because you can see these ordered pairs are listed. But if you'll notice right here, the domain is bracket -1 to 2 with a parentheses, and -3, 1.5 with parentheses. So what that tells me is that the point 2, 1.5 is actually a hole, because the 2 and the 1.5 are open boundaries. So then that's going to switch this to parentheses here. So the way to check this is this domain should be this range exactly, and this range should be this domain exactly. So the properties of the inverse are displayed here. You can switch the ordered pairs, and the entire domains and ranges switch. All right, pause the video and try this one, and then we'll come back together. Okay, this one is really hard to see, but it gives me a chance to explain something to you. So this one I could tell was -2, 1. This one I could tell was -1, 2. This point, I couldn't really read it. So I think I made this, I just picked another point. You can pick any points that are on this graph, and sometimes you might need to pick more than what you're given. So sometimes maybe this point might be a good one because it was kind of hard to tell the right curvature. So you can pick as many points as you need to. But anyway, I picked -2, 1, -1, 2, and 2, 3, and then you switch them and you get 1, -2, 2, -1, 3, 2, and that's how I was able to graph the inverse. And when you're done, from beginning to end, it should look symmetrical about the line y equals x. Okay, so now we'll come back together with the domain. The domain of f and the range of f is from x equals -2 to x equals 2. So bracket -2 to 2. And the range of f, which is this yellow graph, the lowest y value is 1, the highest is 3. So it's got a range of bracket 1 to bracket 3. So that means I'm not even going to look at the graph this time. I'm going to do this domain first by switching it. That would be 1 to 3. Those y coordinates from 1 to 3, and the range should be the x coordinates from 1 to 3, and the range should be the y coordinates from -2 to 2. And then I'm going to check and see if this really does have the same domain I wrote down. 1 to 3, yes. And range -2 to 2, yes. So whichever way you do first, you want to check. You want to make sure what you've written down makes sense, because sometimes people get these numbers backwards and they don't check. All right, now the next thing we're going to do is we're going to learn how to find the inverse of a one-to-one function algebraically. Okay, so these are the steps. You have to replace the f of x with the y, and then you're going to switch the x and y's, just like you switched these x's and y's. And then you're going to solve for y, and then once you have y by itself, you're going to replace the y with the proper function notation, because we lost the function notation temporarily. We've got to put the function notation back. Okay, so if we wanted to find the inverse of this line, the inverse of a line is going to be another line. So this is y equals 3 minus 5x. So we're going to switch the x's and y's for step 2. And now we're going to solve for y. So y is being multiplied by -5, and then there's a 3 being added. So we need to undo that by subtracting 3 from both sides, or just moving that 3 term over. So that's x minus 3 equals -5y. Then we're going to divide by -5. And that gives me y equals, now what I'm going to do is distribute this -5 so it looks like y equals mx plus b. So this -5 belongs to both of these. So 1x divided by -5 is -1/5 x. And -3 divided by -5 is +3/5. So the inverse of a line is another line, so let's put the inverse notation back. So the inverse of f is equal to -1/5 x plus 3/5. And if we were to graph both of these, they would be symmetrical to each other across the line y equals x. All right, now number 2 is going to take a little bit more time. You might see y, it's got 2 x's. So when we replace f of x with y, and we switch the x's and y's, then you will see the problem that we're going to have. And this can be tricky for students, so you may want to just redo this problem off somewhere just to keep doing the same problem over and over again until you understand the steps. See, we want to get y by itself, but we have a problem in that we have 2 y's. So what we're going to do is we're going to cross multiply. So don't know if you've seen me do cross multiplication before, but I'll explain what it is. When you have one fraction equal, it's a property of the equality sign, equal to another fraction. So we'll just call this fraction a over b and that fraction c over d. You can do something called, you can multiply this denominator times that numerator, and you get a times d, and then this denominator b times that numerator, and equal to b times c, and that's called the cross product. So that's called cross multiplying, and it's a really quick way to get rid of the fractions. So whenever you have one fraction equal to another, that's a grouping symbol, you can multiply denominator to numerator. So x times y minus 2 is equal to 1 times 3y. That's called cross multiplication. It's a property of the equal sign. You can do that when you have an equal sign. Okay, now at least we got rid of the fractions. The next thing we're going to do is distribute. Because you have to, why does distributing help us? Well, why? We're trying to solve for y, and it's stuck inside these parentheses. So if we distribute, that'll get rid of that problem. Okay, so now those two steps have given us 3 terms. You see the 3 terms? All right, now we can start moving terms over the equal sign. They're really easy to move over the equal sign. Terms just change signs when you move them over the equal sign. And so what I want to do is I want to get the y terms on the left. It could be on the right. I think students think it's easier if I just always go to the left, and the non-y terms on the right. Okay, so that means that this xy term right here, it's already on the left. All right, and then this 3y term is on the right. It needs to go to the left, so that would become a minus 3y term. And this minus 2x doesn't have a y, so it's going to move to the right side of the equal sign and become a positive 2x. All right, so after we do those things, now we're one step away, and this is really the part where sometimes students forget what to do. So I don't know if I've said it before, but I'll say it now. And many times after, factoring is our friend. Factor out the GCF. They both have a y in common. Remember, you're trying to solve for y. So if you factor out the y, then that becomes y times x minus 3. And what that does, it goes from 2 y terms to just a y times that. If you can remember that, then most people know what to do next. We want to solve for y, we're going to divide. So we're going to divide by x minus 3. And so y equals this. I'm going to go ahead and use inverse notation because I'm running out of room. And there you go. That's the inverse. All right, so let's talk about this one just a little bit more. This is where inverses are helpful. This is a rational function. So if you remember, rational functions have a vertical asymptote and they have branches. All right, and so it's really easy to see the domain because there's a domain restriction. It's not so easy to find the range. So something clever that I do, if I'm asked to find the inverse of f and the domain and range, what I'm going to use is I'm going to use the domain checklist to my advantage. Here's the function. And I'm going to find the domain, which is pretty easy because you don't look at the numerator. All you have to do is look at the denominator. X minus 2 cannot equal 0. So x cannot equal 2. So the domain would be negative infinity to 2 union 2 to infinity. We have a very clear rule for finding the domain. Now the range is not so easy to find, but I don't need to. What I can do, and this is the clever part, is I can go and look at this inverse function and use the domain rule here, and I can see that x can't be 3 here in this denominator. So this domain of the inverse, would be negative infinity to 3 union 3 to infinity. Well, what does that do for me? Well, remember the domains and the ranges switch. So if I have the domain of the inverse, I have the range of the function. And then over here, if I have the domain of the function, I have the range of the inverse. So that's pretty nice. You can use inverses, find the domain, and then switch them. And you don't ever have to do the range. Okay, so these can be tricky. So here's another one, and I want you to try it, but I'm going to go ahead and tell you the steps are not going to change, right? So for these rational function inverses, you're going to switch the x's and y's, and then solve for y. Now when you solve for y, that's the tricky part, but it's the same every time. So when you solve for y, you're going to cross multiply. And then you're going to distribute. And then you're going to get y terms on the left and the non-y terms on the right. And then you're going to factor. And then you're going to divide. So they're hard, but the steps are always the same. So pause the video and see if you can do that. Okay, how did you do? Did you cross multiply? And then distribute. And then this 2xy stays on the left. 5y becomes a minus 5y on the left. 6x becomes a negative 6x on the right. Did you remember to factor out the y? And then did you divide? So a rational function's inverse is another rational function. All right, now if we want to state the domain and the range, remember it's a good idea to state the domain of each of them and then swap them out. Okay, so this domain 2x plus 6 cannot equal 0. So that's x cannot equal negative 3. So negative infinity to negative 3 union negative 3 to infinity. So this would be the range of the inverse. This domain, 2x minus 5, cannot equal 0. So that's x cannot equal 5 halves. So this domain would be negative infinity to 5 halves, union 5 halves to infinity, which means that this range would be negative infinity to 5 halves, union 5 halves to infinity. Okay, so we've done two rational functions, find the inverse in their domain and range. Let's move on to a different function. So you see number 4 is a radical function. All right, so I'm just going to, since I have time on a video, I'm going to show you how you would graph this. So first of all, I'm going to move this so that it's 5x plus 2. Now, something I haven't taught in the transformations, this is kind of a tough one to graph because if you want to use transformations, you could plot points. Always, you put this in the table and get some points and graph it. But if you want to use transformations, if you have a number in front of that x, you actually have to factor that out. So that's tricky because factoring out the 5 doesn't go into 2 evenly. So when you pull out the 5, you just have to say, well, what is 2 divided by that 5? Because you're multiplying. The opposite of multiplication is division. So this is going to factor into 5 times x plus 2/5. So now I know, this is a really tricky one to graph. I know that this is going to shift left negative 2/5. And this is horizontally shrinking it by a factor of 1/5. So that's not really very nice to graph, but it's just going to make it a lot more narrow. So that's good enough. That's all I wanted to do. Okay, so back to our task at hand. You don't have to graph it, but I just wanted to illustrate how to do that. So to find the inverse, you do the same thing. So y equals the square root of 2 plus 5x. All right, so switch the x's and y's. So that's 2 plus 5y underneath there. Okay, so here's y. Y is being multiplied by 5. 5y is being added. 2's adding. And the last thing that's happening to this is the square root. So that's the first thing we want to undo. So we're going to square both sides. So that's x squared equals 2 plus 5y. All right, then we can move the 2 over. So there's 3 terms if you want to think of it that way. You can move that term over. So that's x squared minus 2 equals 5y. And then we're going to divide by 5. And so y equals, I'm going to do the same thing I did with the line so that I can show you what this is. There's an understood one here, and that 5 belongs to both of them. So that's 1/5 x squared minus 2/5. So my inverse of this square root function is this quadratic. Now, this leads us into a problem. I've got a whole bunch of notes on this coming up, But there's a problem because this quadratic, the way it looks like this. You can look at it how it's gone down 2/5, translated down 2/5. So here is my negative 2/5, and it's being vertically shrunk by a factor of 1/5. So it's also very narrow, but it's quadratic. So here's the problem. It's going to look like this, and that's not 1-to-1. So this is not quite the end of the deal. But you can see if you graph both of them, if I just got rid of this branch, this left side of this symmetrical parabola, that looks good. So what we have to do when we have a quadratic inverse is we have to restrict the domain. And it starts at that right branch starts at when x is 0. So that little extra step is what we need to do. Again, I'm going to talk a lot more about that. So hold that thought. Actually, it's next. All right, so number 7, I've got it highlighted. There's just this weird extra step we have to do with quadratic. So this is the quadratic function and its inverse. All right, now we need to go back and forth on this. So this first example, A, actually came from a WebAssign question back in the day. It says find the entire domain on which the function f, this function here, is 1-to-1 and not decreasing. So this is why we had to start the lesson with 1-to-1, because we should know what this looks like right now. And so when I first did this problem in the website, I thought, oh, I don't understand what to do. Well, whenever you're given a quadratic, when you're given a quadratic word problem or whatever, you should know how to graph it, because that will answer a lot of questions, right? So it's quadratic because of the x squared. This plus 8, remember what it does? It shifts it left 8. So this is what f of x is. Okay, so if you graph it, now read this again. It says find the entire domain on which the function f is 1-to-1. Is that 1-to-1? No, it fails the horizontal line test. Okay, so they're telling you what to do. They're saying find the entire domain on which the function is 1-to-1 and it's not decreasing. This is a fancy way for them so that they'll tell you which branch to use. So this branch right here is decreasing. They want you to use the branch that's not decreasing. So they literally want you to just get rid of that left branch. Okay, so now what we just did is restricted this domain to as long as x is greater than or equal to -8. Now, when I first did this, I even myself said, why did they have to say not decreasing? Why couldn't they just say increasing? Well, if they just said increasing here, then that little minimum, that vertex, would not have been allowed to be included, because that's neither increasing nor decreasing. So by saying not decreasing, now we get to include the vertex. So that's why they said that. All right, now once we do that, it says write the domain in interval notation. So I just wrote it this way. I'm going to rewrite it in interval notation. Okay, so that's that. And now I can find the inverse. Okay, so how do we find the inverse? Well, we switch the x's and y's. So that's going to be x equals y plus 8 quantity squared, right? So if I get rid of the square, I'm going to take the square root of both sides. When you take the square root, it's plus or minus square root. All right? Because let me show you. So if I had this equation, x squared equals 4, isn't it true that x could be 2 or -2? So there's both a positive and a negative number that could be true. So if you want to algebraically remember that, what you have to do is when you want to get rid of the square and you take the square root of both sides, when you are the one that takes the square root, it wasn't there before, then you have to account for both possibilities, plus or minus 2. So that's why that's there. Okay. All right, now we're going to get rid of that, but that's true. All right. So we subtract 8 and we end up with let's rewrite it this way. Y equals plus or minus square root of x, and we're going to move that over there, so that's minus 8. Follow me there? Okay, now, if I were to, what does this mean? Okay, well, what this means is y equals positive square root of x minus 8, or it means y equals negative square root of x minus 8. Well, what does that mean? If I were to graph that, that looks like this, down 8 and the upper branch like that. If I were to graph this, that looks like down 8 and the lower branch. Okay, so this fact that we restricted this parabola to the right branch means that we want to, you can see the inverse is the upper branch. So this is what we want. We don't want the negative, we want the positive. Okay, so I'm going to write the final answer here. So the inverse is the positive square root of x minus 8. It looks like that, the upper branch. Okay, so we're going to talk about this a lot more. So we can see from this example that the quadratic function and the radical function, or square root function, we should say, are inverse functions of each other. But what makes this hard and why we're really going to focus on it is because the quadratic is not one-to-one. So we need to switch. We need to, restrict the domain so it's just one branch or the other. Okay, so we're going to come back and do these examples, but I wanted to really give you something that you could study to help with this restricting the domain idea. All right, so here is a guide to help you know how to restrict the domain of the quadratic. All right, so this is the square root function, and over here is the quadratic function. All right, so if you have a square root function that looks like this, let's look at what the vertex is. You see the vertex is 2, 1. You see how it's an upper branch? So this is f of x equals the square root of x minus 2 plus 1. If we use transformations, go right 2 up 1. That's that function. All right. Well, the inverse of that this is the upper, we call it upper branch. The inverse of that is, here's a parabola with just only one branch. The upper branch of the radical always goes with the right branch of the quadratic. Upper branch of the radical goes with the right branch of the quadratic. If you don't believe it, here it is. Both of them are graphed on the same coordinate plane. All right, now we can use inverse techniques, switch the x's and y's, solve for y, but since we've got the graph, I can go ahead and write the inverse because I'm looking at it. All right, and we know translation. So the parent function is x squared. Well, this 1 means I'm moving to the right 1 squared. This 2 is up 2. But then you have to put a comma. We want the right branch, so that you would have to say, comma, x has to be only greater than or equal to 1. So we restrict the domain. All right, let's do it again. We got 3 more examples. Hopefully you'll get it by then. Just looking at these relationship between the radical and the quadratic. All right, now this is a weird one. Let's see. This looks like it has a vertex of -2, 1 again. But this time it's the upper branch, but it's been reflected over the y-axis. So this is going to look like f of x. Let me put the inverse notation there. F of x equals, when you have a reflection of the y-axis, it's affecting the x's. So there's a -1 in there with the x. And then it's being shifted left 2. So that would be an x plus 2. You need parentheses and then plus 1. Okay, so you're not going to have to do this. I'm just doing this quickly. What you need to remember is this is the upper branch of that function. it again is going to go with the right branch of the quadratic. Upper goes with right. Now let's see, this one looks like it's got the, yeah, this is 1, -2, so see how the vertexes switch, the ordered pairs? And so this would be, and it's being flipped upside down over the x-axis, so this would be inverse of f is -1, x minus 1 quantity squared minus 2. So these two are inverses, but what's more important, notice that it's the right branch. And this quadratic has been restricted by just the right branch, so it starts at 1. X is greater than or equal to 1. And there's your evidence. All right, so the takeaway is you can just memorize the right branch of the quadratic goes with the upper branch of the radical. All right, let me do 2 more examples. So here is a radical. See how that's the lower branch of the radical? And that is, looks like that is 1, 2, 1, 2, 3. Okay, so that's vertex 2, 3. So what this would look like would be f of x equals, it's been flipped upside down, so that's negative square root of x minus 2 plus 3. That's the lower branch. So remember it's plus or minus, the negative is the lower branch. So the lower branch of this radical goes with the left branch of that quadratic. So that's the part that you're going to memorize. Now just to have the equation, 1, 2, 3, 1, 2, there it is, 3, 2. See how the ordered pairs switch? And this is the left branch of a regular old quadratic. So this is x minus 3 quantity squared plus 2, but this time x has to be less than or equal to 3. So I've restricted that domain. That's the left branch. So this restriction is always going to come from the x coordinate of the quadratic's vertex. And there it is. If you don't believe it, they are inverses of each other. Left goes with lower. Lower goes with left. All right, let's do this last one. Okay, so here is a radical function that has vertex -2, 1. So, and it's the lower branch, so that means it's a negative there. Square root of x plus 2 plus 1. So the inverse is going to be lower branch, that negative goes with left branch of quadratic. Okay, so that's going to be 1, -2. That checks out. And this is it's been flipped over the y-axis. So that is going to be -1, x minus 1 quantity squared minus 2, where x is less than or equal to 1. Okay, now I'm not going to go back and edit the video because this illustrates something. Sometimes one function is easier to kind of understand than the other. So when I was doing this one, it's a lot easier for me to notice that this is an upside down parabola. And I know it's been reflected over the x-axis. So that means a -1. And that helped me to see that I forgot that this radical right here has been reflected over the y. So everything is opposite. If this inverse function has been reflected over x, then that one must have been reflected over the y. And I remembered I didn't do that, so I need to fix this. So when you're reflecting over the y, remember the -1 is in there with the x. So you have that -1 there. And this -2 does show up as x plus 2. So I just forgot that -1 in there. And I'm not going to edit it because that's really common, and that's the benefit of inverses. Sometimes one function is easier to think about than the other. All right. Okay, I hope you endured that. Go back to where we were on the back of the second page, and this is what you're going to be asked on the test, and hopefully now it will be easier to understand. Okay, so it says find the inverse restricting the domain if necessary. So first of all, you're given a radical function. Do you know whether this is the upper branch or the lower branch? It's the upper branch because I don't see a minus there. So that means upper branch of the radical. That means that the inverse, we're talking about the right branch of the quadratic. Okay, so we're going to do that. We can see that right off. So let's actually find the inverse. That's y. So we're going to change that to x equals square root of y minus 2 plus 1. And we need to solve for y. So move that 1 over. That's x minus 1 equals the square root of y minus 2. Square both sides. And you don't need to multiply this out because we want our quadratic to be in vertex form. All right, now we'll add 2 and we get x minus 1 quantity squared plus 2 equals y. All right, so our inverse would be inverse notation, f inverse of x equals x minus 1 squared plus 2. But the problem is that's this, right? We just want the right branch. So we need to restrict this domain to x is greater than or equal to 1. It's always the x coordinate of the vertex. All right, let's go the other way. F of x equals negative square root of x minus 1 quantity squared plus 2. Okay, so right now, that function is not one-to-one. We can graph it. We should be able to know that it's going right 1 and up 2. And that is this. All right, so I have to tell you which branch to use. So I've kind of done that here. I've already started it. X has to be greater than or equal to what? Well, the vertex we know is 1, 2. So x has to be greater than or equal to 1. That's the right branch. I'm going to erase it. Now it's 1-to-1, and now it has an inverse. Which part of the radical will it be? Well, this is the right branch of the quadratic. So that goes with upper branch of the radical. All right, so now I'm going to switch the x's and y's. I'm going to put that understood 1 in there to make sure I don't mess up. We don't deal with that right now. All right, so I need to solve for y. So the last thing that happens, the first thing is minus 1, second squared, third multiply by negative 1, last thing add 2. So first thing I'm going to do is subtract 2. So that's x minus 2 equals negative 1 times y minus 1 squared. We can't distribute that negative 1 in because we have to deal with the exponent first. So I'm going to divide out the negative 1, which makes that negative x plus 2 equals y minus 1 quantity squared. Now I'm going to take the square root, and that's plus or minus square root of 2 minus x equals y minus 1. But I already know I need the upper branch. So I'm not going to need both the plus or minus. I just need the positive, the upper branch. So last thing is I'm going to add 1. So 1 plus the square root of 2 minus x is equal to y. So the inverse function, it's a radical function. The square root function would be the square root of 2 minus x plus 1. All right. You can pause the video if you want and try this on your own. I'm going to just take it step by step just in case you need it. All right. Here we go. We are given a quadratic. See, knowing what these look like is very helpful. So that's 1, 2, 3 to the right, up 2. The vertex is 3, 2. And this time, I see how I have both branches, but this time I only want the left branch. Okay, so I have to tell you that. Or you can pick, but if it says x is less than or equal to, that's the left branch. And it has to be x is less than or equal to 3. So then this is the part you memorize. Left branch of the quadratic goes with the lower branch of the radical. So if I solve for y. Here, switch the x's and y's. Okay, move that 2 over. That's x minus 2 equals y minus 3 quantity squared. Square root both sides, and that's plus or minus square root of x minus 2 equals y minus 3. So right here, you need to understand we're talking about the radical starburst. This positive is the upper branch, and that negative is the lower. I can't have both. It's not a function. But this left branch means lower branch. So this one is going to be a negative. The negative in front of the radical is the lower branch. All right, so last step, I'm going to add 3. And this time I'm going to write it this way. Y equals negative square root of x minus 2. And that minus 3 go over there, plus 3. So I'm going to put it afterwards there. So my inverse is this negative square root of x minus 2 quantity squared plus 3. That's the lower branch. All right. Last one. If you want to, you can pause it. And I'll come back with you. All right, this one was awfully tricky because of all the negatives. So first thing I did is I made my negatives be understood negative ones. So x equals negative 1 times the square root of negative 1y minus 2 quantity squared plus 1. All right, I moved the 1 over. That became x minus 1. And then I squared both sides. Now this is where it got interesting. So you have to remember that negative 1 times this, when you square this, this square actually goes to both of these. So negative 1 squared becomes 1. It kind of just goes away. It's an understood 1. And the square root of negative 1 y minus 2 squared, that goes away. So you might say, where did that go? Well, it got squared out. Negative 1 squared is 1. Okay, so we have x minus 1 quantity squared equals negative 1y minus 2. All right, now I'm going to add 2 to the left. So that's x minus 1 quantity squared plus 2 equals negative 1y. Okay, now I need to divide by negative 1. And just like before, even though this is complicated, that negative 1 goes to that term, and that negative 1 goes to this term. So 1 divided by negative 1 is negative 1, x minus 1 squared, and 2 divided by negative 1 is negative 2. All right, so we did it. So the inverse of this function is negative x minus 1 quantity squared minus 2, but not so fast. We have one more thing to do. We have to restrict this domain because this is a quadratic and it's not 1-to-1. This looks like it has a vertex at 1, negative 2, and it's the upside down. So we have to figure out which branch it is. Well, that part's not hard if you understand the memorization. This negative here at the beginning of this radical is the lower branch. So we need the left branch. All right, so there it is. So we need to restrict this to x is less than or equal to 1. So if it's a left branch, it's going to be a less than. If it's a right branch, it's going to be a greater than. If it's just going to be the x coordinate of the vertex. All right, so it doesn't get harder than that one, but that's the emphasis in this class is really understanding the quadratic function and its inverse, the radical function or square root function.